3.4 Adiabatic Processes IM. Associate Professor Yusri Yusup from the School of Industrial Technology, University Sains, Malaysia. The outline of this video is as follows. We will discuss several key concepts related to how air behaves as it moves vertically in our atmosphere. We will start with an introduction to adiabatic processes, which are changes that occur without any heat being added or removed from a system. Then we will define what we mean by an ideal air parcel, a concept we use all the time to simplify our analysis. From there, we will derive and understand the dry adiabatic lapse rate, which we call gamma sub d. This will lead us directly into a discussion of potential temperature, or theta, and why it is so important as a conserved quantity. We will also get familiar with some essential tools for atmospheric scientists, the thermodynamic diagrams, specifically the pseudo-adiabatic and Skew T log P charts. Finally, we will apply these ideas to a real-world example. What happens to the air that gets compressed into an aircraft cabin? Let us dive into one of the most fundamental concepts in atmospheric thermodynamics, the adiabatic process. An adiabatic process occurs when a material, like a parcel of air, changes its physical state, meaning its pressure, volume, or temperature, without any heat being added to it or taken away from it. In the language of our first law of thermodynamics, this simply means the change in heat, which we call Wood Q, is equal to 0, and O heat in and no heat out. Now, if you imagine compressing a gas adiabatically, you are doing work on that system. That energy has to go somewhere, right? It increases the gas's internal energy, and we see this as a rise in its temperature. This is a key reason why, on a pressure-volume diagram, the curve for an adiabatic process, called an adiabat, is steeper than the curve for an isothermal process. For the same volume change, the adiabatic compression results in a higher final temperature and therefore a higher final pressure. This slide presents figure 3.5, which gives us a great visual comparison between an isothermal and an adiabatic process on a PV diagram. Let us imagine we have a system, perhaps a parcel of air, starting at point A. If we compress it while keeping its temperature constant, we follow the curve labeled AB, which is an isotherm. Now, if we compress that same parcel adiabatically, meaning we do not allow any heat to be exchanged with the surroundings, we follow the curve AC, the adiabat. You can immediately see that the adiabat is much steeper. Why is that? Well, during adiabatic compression, the work we perform on the parcel increases its internal energy, which in turn raises its temperature. A hotter parcel at the same volume will naturally exert more pressure. So for the exact same change in volume, the adiabatic process results in a higher final pressure and temperature than the isothermal one. This is a crucial distinction that we will build upon next. When we think about how the atmosphere mixes vertically, it is tempting to picture individual molecules bouncing around. However, that kind of molecular mixing is really only significant in a very thin layer right near the ground, or way up high above 105 kilometers at the turbopause. In the vast space in between, vertical mixing is dominated by the movement of much larger chunks of air we call air parcels. Now, an air parcel is not something you can actually see or touch. It is a very useful theoretical tool, an idealized tiny blob of air that we imagine moving around. Nenyan. To make our models work, we have to make a few key assumptions about this parcel. For example, we assume it is thermally insulated from its surroundings, meaning it does not exchange heat with the air around it. We also assume it moves slowly enough that its kinetic energy is negligible. These idealizations help us understand the fundamental physics of vertical motion and atmospheric stability, which we will explore next. To understand how air moves and mixes vertically in the atmosphere, we often use a simplified concept called an ideal air parcel. Think of it as a small self-contained bubble of air. First, we assume this parcel is thermally insulated, meaning no heat is exchanged with the surrounding environment. Its temperature changes are purely adiabatic, resulting only from compression or expansion as it moves up or down. Second, we assume the parcel is always in pressure equilibrium. This means its internal pressure instantly adjusts to match the outside environmental pressure, at any given altitude. Finally, we assume the parcel moves slowly enough that its kinetic energy is negligible compared to its total internal energy. Now, are these conditions ever perfectly met in the real world? Almost never. However, this idealized model is an invaluable tool that helps us understand some of the most fundamental processes in our atmosphere. Let us explore one of the most fundamental concepts in atmospheric science, the dry adiabatic lapse rate. We represent this with the symbol gamma sub d. This is the specific rate at which a parcel of dry air cools as it rises or warms as it sinks, all without exchanging any heat with its surroundings. The process is adiabatic. We derive this from the first law of thermodynamics, applied to an atmosphere in hydrostatic balance. Essentially, we state that the dry static energy, which is the sum of enthalpy C sub P times T and geopotential phi, remains constant for this process. This leads us to a beautifully simple relationship. The dry adiabatic lapse rate gamma sub d, which is defined as the negative change in temperature with height for the parcel, equals the acceleration due to gravity, g, divided by the specific heat capacity of dry air at constant pressure, Ce sub p. So, as a parcel rises and expands, it cools at a constant rate, and as it sinks and gets compressed, it warms at that very same rate. So how do we get a specific number for the dry adiabatic lapse rate, or gamma sub d? We simply plug in some well-known physical constants. We use the acceleration due to gravity, g, which is about 9.81 meters per second squared, and the specific heat of dry air at constant pressure, Ce sub p, which is approximately 1004 joules per Kelvin per kilogram. When we perform the calculation, dividing g by C sub p, we get a value of about 0.0098 Kelvin per meter. Now, in meteorology, we usually talk about temperature changes over kilometers, not meters. So we convert this and it becomes 9.8 Kelvin per kilometer. For most practical purposes, we can round this to a very convenient 10 degrees Celsius per kilometer. It is absolutely crucial to remember this is a theoretical process rate for a rising or sinking dry air parcel. It is not the same as the environmental lapse rate, which is the actual measured temperature profile of the surrounding atmosphere. Let us introduce a really powerful concept in thermodynamics called potential temperature, represented by the Greek letter theta. The definition is a bit of a what-if scenario. Imagine you take an air parcel from its current pressure and temperature and you move it adiabatically to a standard reference pressure, which we usually set at 1000 hectopascals. The temperature the parcel would have at that standard level is its potential temperature. So why is this hypothetical value so important? Its real significance lies in the fact that potential temperature is a conserved quantity during adiabatic motion. This means that as an air parcel rises and cools or sinks and warms, its potential temperature does not change. This makes it an excellent tag or label. We can use it to trace the origin and history of an air parcel, which is incredibly useful because many atmospheric processes are very close to being adiabatic. The mathematical relationship between temperature, pressure, and potential temperature is incredibly useful, and it all starts with the first law of thermodynamics for an adiabatic process. We begin with the expression stating that the change in heat is zero, which can be written as Cp dt minus alpha dP equals 0. Next, we use the ideal gas law to replace the specific volume, alpha, with RRT over P. After a little algebraic rearrangement, this gives us a differential equation, dt over T minus the ratio R over Cp times dP over P equals 0. The final step is to integrate this equation. We integrate from an air parcel's initial state, defined by its pressure P and temperature T, to a reference state where the pressure is P naught and the temperature is the potential temperature, theta. This integration yields the famous Poisson's equation, theta equals T, multiplied by the ratio P naught over P, all raised to the power of R over Cp. For dry air, that exponent, ER divided by Cp, is a constant value of about 0.286, a number you will become very familiar with. Thermodynamic diagrams are some of the most powerful tools we have as atmospheric scientists. Think of them as a special kind of graph paper designed specifically for the atmosphere. They allow us to plot vertical profiles of temperature and dew point, which we call atmospheric soundings, and visualize complex thermodynamic processes. The real genius of these diagrams is how their axes are set up. They are intentionally distorted so that key processes like a parcel of air rising and cooling adiabatically appear as simple, easy-to-follow lines. We will look at two important types. First is the pseudo-adiabatic chart, which is an older design. While historically important, its layout can make different soundings look very similar. This led to the development of the Skew T log P chart. This is the modern standard you will see everywhere. Its clever design skews the temperature axis, which makes it much easier to analyze the stability of the atmosphere with precision. This slide presents figure 3.6, which is a schematic of what we call a pseudo-adiabatic chart. This was a very common tool used for meteorological calculations for a long time. Let us break down its structure. The vertical axis represents pressure, but it is on a distorted scale, specifically pressure to the power of 0.286, which ensures that pressure decreases as we move upward, just like in the real atmosphere. Now, notice the lines. The vertical lines are isotherms, meaning lines of constant temperature. The lines that slope upward and to the left are the dry adiabats, representing constant potential temperature, or theta. While this chart is historically important, it has a practical limitation. When you plot actual atmospheric soundings, they tend to cluster within a very narrow range of angles, making it difficult to spot subtle but significant variations. This is the key reason why the Skew T log PE chart, which we will see next, was developed to overcome this issue. Now let us look at the Skew T log P chart, which is a fantastic tool engineered specifically to make atmospheric soundings easier for us to interpret. The coordinate system is quite clever. The vertical axis represents pressure on a logarithmic scale, specifically as negative natural log of P, which means pressure decreases as you go up the chart, just like in the atmosphere. The horizontal axis is simply temperature. The key feature and where the chart gets its name is that the isotherms are skewed. Instead of being vertical, they are straight parallel lines that slope upward from left to right at about a 45-degree angle. The dry adiabats, which are lines of constant potential temperature, are slightly curved and run from the lower right to the upper left. The genius of this design is that the angle between the isotherms and the dry adiabats is approximately 90 degrees. This makes any small differences between the actual temperature profile and the adiabatic lapse rate highly visible, which is crucial for analyzing stability. This slide presents figure 3.7, which is the schematic of the Skew T log P chart. Now, we just discussed how older charts had a problem where atmospheric soundings would often bunch together, making them difficult to interpret. The Skew T chart is the solution to that problem. You can see its key features here. The isobars, or lines of constant pressure, run horizontally. The isotherms, which are lines of constant temperature, are the straight lines that are intentionally skewed, sloping upwards from left to right. Finally, the dry adiabats, representing constant potential temperature, are the slightly curved lines running from the lower right to the upper left. The genius of this design is that it maximizes the angle between the isotherms and the dry adiabats to nearly 90 degrees. This separation makes it much easier for us to plot and analyze atmospheric profiles, because small but important variations in temperature become much more apparent. Let us apply what we have learned about adiabatic processes to a very practical example: the air inside an airplane cabin. Imagine we are at a typical cruising altitude where the pressure is 250 hectopascals and the outside air temperature is a chilly -51 degrees Celsius. Now, we bring that air inside and compress it to the cabin pressure of 850 hectopascals. To find the new temperature, we use our Skew T ln PE chart. First, we find the starting point at 250 hectopascals and -51 degrees. The dry adiabat running through this point tells us the potential temperature is about 60 degrees Celsius. We then follow that same dry adiabat down to the 850 hectopascal pressure level. Reading the temperature at this new point gives us a surprising result, 44.5 degrees Celsius. That is incredibly hot. This is why aircraft have to significantly cool the outside air before it is comfortable for us to breathe. Let us bring everything together now with a summary of the core concepts from this section. First, we have the adiabatic process, where a change happens with absolutely no heat exchange with the surroundings. All temperature changes are purely due to the work of expansion or compression. We apply this idea using our air parcel model, which is an idealized, thermally isolated bubble of air. It is a fantastic tool that always maintains pressure balance with its environment as it moves. When this dry air parcel rises, it cools at a constant rate called the dry adiabatic lapse rate, which is about 9.8 Kelvin per kilometer. To track these parcels, we use potential temperature, a conserved quantity that acts like a unique identifier for an air mass as long as the process is adiabatic. It is incredibly valuable for tracing where air has come from. Finally, we visualize all these relationships on the Skew T log PE chart, the standard diagram for analyzing atmospheric temperature profiles and stability. These concepts are truly the foundation for much of what we will discuss next. Let us think through these questions together as they get to the heart of using thermodynamic diagrams. For the first question, if an air parcel sinks adiabatically, it means no heat is exchanged with its surroundings. By definition, potential temperature is the temperature a parcel would have if moved adiabatically to a standard pressure level, so it remains constant during this process. However, as the parcel sinks from 800 to 1000 hectopascals, it is moving into a region of higher pressure. This increased pressure compresses the parcel, doing work on it and increasing its internal energy, which we observe as a rise in its actual temperature. Now for the second question, the nearly 90-degree angle between isotherms and adiabats on a Skew T chart is a clever and intentional design choice. This large angle of intersection makes it much easier for us to visually distinguish the slope of an environmental temperature sounding from the slope of the adiabats. This visual clarity is the key practical advantage, as it allows for a much quicker and more accurate assessment of atmospheric stability compared to older charts where the lines were almost parallel.